Well, during these 45 minutes, we will share a summary of a technology review done by Gautam, in which cooling technologies are summarized and analyzed for understanding the implications in global warming, and we will analyze different possible solutions. We will also talk about sustainable cooling, one of the most important milestones for climate change mitigation. We will combine this information with a systemic view in order to show the complexity of these multidisciplinary reports and how crucial are these reports in a global warming fight. Other critical facts that we will show is that these reports need to be disseminated and understood by all governments and mainly by all the population. So let's start. I will skip the agenda. I just introduced the work we will present now. So let's think about local industry and consumer culture. Both generate local greenhouse gases emissions in a local basis. But all the local emissions are finally global. The gases are mixed all together. So this produces global climate change. So I am showing in several blocks. So what we need is to achieve local mitigation actions, but it's good to understand that, for example, why would a government invest its limited resources in local mitigation actions if the benefits will be in the future and extremely low and global? So that might be a good question to ask. And also, who pays for that actions and who benefits? So let's continue. So the damage generated by climate change is local. Let's say that it's local in the present. So right now, and that damage generates suffering in the population. So the governments. So only to clarify, this kind of blocks refers to that in each country these blocks might apply. So the global blocks are not with this stack of blocks. So well, after the damage, local governments must act with adaptation actions, helping the people, investing money. And well, in parallel, global climate change enables the validation and verification of several mathematical models and also past mitigation actions. So this helps to understand the global warming. So that helps global organizations, to design new strategies, and they also use new case studies from new damages produced in different parts of the world. And with all this, they generate specialized global reports combining adaptation strategies and mitigation strategies. But well, we have also third-party climate change analysts and companies that generate their own technology reviews, for example. So this is highlighted because we are going to talk about one of these kind of reports about cooling, in this case, space cooling. And well, these kind of reports help to adapt global strategies to local strategies. And after this, local governments can understand, they can understand with some help the recommendations for local action. Well, and they also, we can say that they also receive some top-down pressure. And then, well, we are closing this loop with some investment, and some local mitigation actions are done in several countries. So after that, we can introduce delays almost everywhere, and to understand the relationship between the blocks here. For example, if more local adaptation actions are taken, we will get less suffering of the people. And here we also have a negative feedback, a negative relation, in which with more mitigation actions, less emissions. The changes in local industry and consumer culture changes for best. So we can think about a general question: if these reports, the very complex reports and very long reports, can guarantee these mitigation actions. Well, let's remember this question. So, which are the main stakeholders? Well, as I said before, international organizations, governments, companies, and mainly the planet. That's obvious. The rationale for this table, well, you can read the details after the presentation, but it's good to have this in mind. So Gautam, please.
Yes, thank you. So we look at what the problem is of cooling. The presentation focuses on space cooling, but we can look at cooling in general to start with. Cooling is vital for both health and prosperity. However, the problem is that business as usual, the way we are cooling, will be a disaster for the planet. So we have this contradiction. Something that's good will cause also damage. So getting cooling right, to do it right, to get the cooling without damaging the planet is a problem, but it's also an opportunity. The next slide. One area where cooling would help is reducing food loss. Right now, 630 million tons of food is lost in developing countries, mostly from the farm and the harvest and getting to the consumer. Ironically, a similar amount of food is wasted in the developed countries, but this is at the supermarket and at the household level. So it's loss. It doesn't come to the people who are hungry, and it's thrown away from the people who are already well fed. So we have a double irony. But the improving cold for storage and things will help the left-hand side of the diagram, which is the people who are not getting the food because it gets wasted or lost along the way. Next. Health and cooling. This report is from 2019, the year before the pandemic, and they said the lack of adequate cold storage and refrigerator transport meant that over 1.5 million people were dying from diseases that could be prevented by vaccines. So a significant number. And as of yesterday, about half of the world population has received at least one dose of COVID-19 vaccine, but only 2.8% of people in low-income countries have received one dose. So there's a big gap between access to vaccines, and some of it is related, a lot of it is related to access to cold, to have the vaccine to be sent to the people who need it, who might not have refrigerated locations and refrigerated transport. So cold and health is very important move. Next slide. When I was, in the 1960s, every poor country was hot. So it was irony that, and I was convinced that, we hot people were lazy people, so we were poor. But an example of it is not the case, and Singapore was the first country to go from third world to first world, and it's now has one of the highest, it's a very hot place, but it has one of the highest GDP per capita in the world, slightly higher than the US. Next slide. And sorry, air conditioning was a part of how Singapore could become a better place to live and become more productive. Obviously not the only factor. The problem, historically over the last decades, the number of air conditioners has increased from about 500 million in 1990 to about 2 billion now, and is projected to increase as more hot hot countries, people become more prosperous and will demand more air conditioning, but also because the planet is getting hot. So we'll need more air conditioners. And this is part of the problem. Next slide. Another problem is with increasing urbanization, we have to note that the urban areas are hotter than the surrounding areas. It's because of a phenomenon called urban heat island. And sometimes a place may be very good climate, but once a city is built there, then it gets hot and it needs cooling. Los Angeles in California is a very good example of such a place. But there are many other cities. You probably know some of them. Next one. This is a graph which shows on the left-hand side the cooling demand in 2016 in something called cooling degree days. And obviously the part that is red is the part that's hot. And the right-hand graph is something different. It shows the increasing cooling demand in the Western Hemisphere. And again, you see that the graph on the right-hand side is basically the color means different, but red means 400 on the right-hand side. It's basically a 15% increase in cooling degree days in the next 3-4 decades because of climate change. So the places that are green now will be yellow and red later on. Next slide. And deaths from extreme heat events will also increase, which is to be expected, unless we can do adaptation and prevent this. Next slide. There are many ways of cooling people and cooling things. And mechanical fans are relatively recent, but fans have been around for thousands of years for cooling people, moving the air. Also old techniques are evaporative cooling, more recent 19th century absorption cooling, but the dominant one is vapor compression, which is number 4 on this list. And new technologies include solid state cooling, which I will not mention too much. So let's focus on vapor compression, which is the most common. Next slide. Vapor compression requires a refrigerant which is compressed and then expanded, and this is generates cooling in things from refrigerators, air conditioners, and all sorts of other industrial and commercial cooling equipment. And there has been an evolution of refrigerants. The first generation, before 1930, was anything that worked. Second generation was chlorofluorocarbons that were inert, non-toxic, and very efficient. And then they realized in the 1980s that this was damaging the ozone layer. So the third generation was substitutes for the CFCs that were less damaging, that didn't damage the ozone layer or less damaging. And then the fourth generation, which we'll come to in the next slide. Next slide, please. So the early second generation was CFC, chlorofluorocarbons, of which the main one was called R12, which is defined to have an ozone depleting potential of 1 by definition, how much it damages the ozone layer. All other gases are measured compared to R12. And one of the replacements for R12 was R22, which is a hydrochlorofluorocarbon. It doesn't have a 0 ozone depleting potential, but it has a low one, much smaller. Then people notice that these gases also cause global warming. So on the right column is global warming potential. R12 is 10,000, R22 is 1,700. Then the third generation, the other are hydrofluorocarbons that have no chlorine atoms, so no ozone depleting potential, but they also have high global warming potential. So finally, the world said, all right, besides removing the ozone depleting substance, we have to remove the refrigerants that are warming the planet. So let's move to the green ones, which are in the bottom, which have 0 ozone depleting potential and very, very low global warming potential. But we have to be careful because some of them are toxic, like ammonia, and some of them are flammable, like the hydrocarbons. Next slide. Starting in the 80s, there was consciousness that these chlorofluorocarbons and other gases were damaging the ozone layer, and the world reached a historic agreement in 1987 in Montreal to start to reduce these emissions. And as you can see on the graph, left graph, the emissions went way down from 1990. They still haven't gone to zero, but they have gone to a low level. On the other hand, however, the ozone layer, the stratospheric ozone was getting worse. As you can, it going down in this scale is getting worse. So it got worse. It stopped getting worse around 1990, but it didn't improve. So we are still having high levels of ozone in our, and ultraviolet radiation on our surface, because the ozone layer above us is depleted. On the right bottom corner is the ozone concentration is measured by Dobson units, and that's the instrument that Dobson used in almost 100 years ago to measure this. Okay, so we just remember it. Next slide. Shows this is the map of, weather map of Argentina, showing the radiation, ultraviolet radiation levels from 2 years ago on the left, and yesterday on the right-hand side. And we were told that there's an ozone hole over the South Pole, but in this map you can see that red is bad and purple is worse, that it's worse in the north than in the south. So whatever is happening is affecting the ozone layer. Thinning is uneven, and the radiation, ultraviolet radiation, is very high even in the northern part of Argentina and Paraguay, Brazil. So we still haven't resolved. We've stopped emitting ozone depleting substance, but we still have a problem. Next slide. So in order to have sustainable cooling, we have to solve 3 problems. The bottom one is to make sure that people benefit from the cooling, which we call sustainable development. And we need to protect the ozone layer, and we need to mitigate climate change. So we have to do all 3 together. Next slide. So let's try to quantify the problem looking at one area of cooling, which is residential cooling, air conditioning. By 2030, half of the world population will be in hot climate. Fortunately, Latin American and the Caribbean is not very hot. So, I mean, you might disagree, but in compared to Africa and Asia, it's less. There's more nice climate. But anyhow, by 2050, the residential cooling demand will increase 3-fold globally and 5-fold in developing countries, which are hotter. We have 1.5 billion room air conditioners today, and this is expected to triple if we see the trend. And a technological thing is even the most efficient air conditioners today are only reaching about 14% of the theoretical maximum efficiency. So this is the problem, a part of the problem. Part of the solution is better, and here you need a systems view. You say the problem is air conditioning, but the solution is very much broader. Better urban design, better street alignment, more vegetation, less urban heat island, and all of these can be addressed. Second item, better thermal design of buildings, so the buildings don't heat up so much and the cooling demand is decreased. Then higher efficiency in cooling, which would be the more linear thing. The air conditioner could be much more efficient. And finally, on the bottom of the thing, it's important that because these air conditioners and refrigerators include refrigerants that are damaging the ozone layer and causing global warming, we should have programs to recover the refrigerants so they don't get liberated at the end of the life of the equipment. Next slide. This is an example of street alignment. If the streets are east-west, then the buildings can be better shaded for sun to reduce the cooling load, and they can also admit the sun in winter to reduce the cooling loads. So building orientation is basically a zero-cost item that can reduce cooling and heating demand. Next slide. This is building thermal envelope. You can you can reduce the cooling load dramatically by adding insulation, and one area is roof insulation, which is shown here in this house under construction. Next slide. And wall insulation can greatly reduce the heat, the cooling demand, and also the heating demand in a climate like Buenos Aires, where you have both winter and summer. So it helps in both climates. Next slide. This is a complicated slide. Each vertical bar is a different country. And let's focus on the one I have circled in red, which is Thailand. There's a green dot on the top, which is the most efficient air conditioner sold in Thailand. The red dot on the bottom is the least efficient one. The blue rectangle is the range of equipment that one can buy. But the point here is that there's a blue dot at the bottom of the blue rectangle. That is the average sold. So what you find is the average sold, and this is for Thailand, but it's the same for all of those other countries, is close to the minimum. So even though there's a high efficiency, relatively high efficiency equipment available, most of the people are buying near the bottom of the efficiency scale. So that's one problem. Next slide. We received, my company, MGM Innova, received a support by a Clean Cooling Collaborative, which is a global organization promoting clean cooling and sustainable cooling. And they sponsored a project for us to Latin America and the Caribbean. And we focused on commercial and industrial cooling. This is because we were looking at, from the private sector, what private sector could invest in to improve their cooling performance. We reviewed alternatives to vapor compression systems. Vapor compression is what I said was the main technology. We looked at evaporative cooling, which is old technology, absorption refrigeration, which is also relatively old, well-known technology, seawater air conditioning, which is a relatively new idea, is that the seawater at the bottom of the sea is much colder, and if you can bring it up and circulate it, you can cool houses or buildings on the seaside, and this has a big potential in the Caribbean islands and also in the coastal areas of the Gulf of Mexico, Pacific Ocean, the northern part of South America. Solid state cooling was another thing which is sort of not quite technologically ready. There is not that much technology around, but has a lot of promising future. We looked at the relationship between heating and air conditioning because there are things that you do to reduce cooling, but also benefits heating. Heat pumps is an example that, for instance, my house has a heat pump that can be used for heating and cooling, and it's efficient in both. It's more efficient than gas heating, and it's an efficient air conditioner, so it's also good for cooling. And there is interaction between lighting, air conditioning, and refrigeration, which we also studied. Next slide. Because we were looking for street-wise practical solutions, and not just theoretical things, so we looked at application-specific alternatives. We looked at what can you do in specific situations. So we looked at building air conditioning, and we looked at different solutions within building air conditioning. We looked at district heating and cooling. District heating is well known, but district cooling is, when you, city like Copenhagen or Moscow or Beijing, they have central generation of heating and pipes running under the city, sending heat to heat the places. District cooling is much less common, but you could generate heat in a central location and then send the cold water, usually, to buildings around the central location and use it for cooling. Why would you do that? Because the heat source could be waste heat from some process. So a power plant in Medellin, in the electric company, has a district cooling system serving the central part of the city of Medellin. So that's the first example in Latin America, but it has a reasonable amount of potential. Then we looked at commercial refrigeration, and we focused on supermarkets as something that's replicable because there are chains. So if you find a technological solution, you can apply it to many, and there are different needs. You have freezers, you have refrigerators, you have liquid bottle dispensers, bottle coolers, and you have space refrigeration. And some of the solutions are really out of the box. Like there are companies now that are saying, we'll eliminate the local supermarket when we deliver directly from the warehouse to the end consumer. So you have some solutions where you actually disappear. You eliminate the need for the distribution, the supermarket freezers, because you're going from a higher level of aggregation to the end user. And because we were looking for practical solutions, we also reviewed extensively manufacturer technology offerings. What are the manufacturers offering in terms of clean refrigerants and high efficiency perform equipment and different applications. So this was a very detailed part of the review. Next slide. These were our main conclusions. This is a very detailed report, so I'm going to highlight, sort of mention them. One was that recovering refrigerants from equipment end of life is very important because there's a big opportunity of good recycling, so you don't throw the refrigerant away and damage the climate and ozone layer. And the other thing is important, that energy efficiency is more important than refrigerants. Meaning what? That refrigerants have global warming potential, but the electricity that the refrigerator and air conditioners use, that means more carbon dioxide emissions at power plants. And this is more important because you can save more, reduce emissions of carbon dioxide, and that's more global warming than the refrigerant leakage. Both are important, but one is more important than the other. So if you just go to green refrigerants and say, well, I'm going to use a very nice refrigerant, but my equipment is not efficient, you're losing. So then we found a few other things that are like things not to do, and these are important to know also. There is very little scope for ground source heat pumps in Latin American countries. I don't think we have time to get to what ground source heat pumps is now, but it's a technology that we can basically avoid and not worry about in our region. The market for evaporative cooling is very limited. It could be explored. It only works in hot climates, but because you need water and you have a desert which could be hot and dry, but you don't have the water, so might not work so well. Absorption cooling may be an attractive alternative for building air conditioning and industrial refrigeration. Absorption cooling works by taking heat, and it can be waste heat, so that's good, and generate cold from that. So district cooling, which is where you generate cold at a single location and distribute it, that has a good potential, especially seawater air conditioning has a big potential. But there are some drawbacks also, because it's a chicken and egg thing. You need to design and offer the system, but you also need the sufficient number of clients and buildings to sign up in order to make the system worthwhile. So how do you do it? You have to build the supply, and then you don't have anybody to sell it to, or people demand it, but the supply is not there. So it's an interesting problem. Then there are other options, but other technologies, specific technologies for supermarket refrigeration, air conditioning, very interesting. Because technology is changing, the advances need to be tracked. We used an index that's used by NASA called Technology Readiness Level, and we basically saying where certain numbers, 8, 9, 10 are investment grade, but up to 7 is still not market ready. So we should keep track of it, but not promote it right now, and so on. So there are techniques there are things that a private investor cannot do, but states can do. For instance, there are many countries that require minimum efficiencies for refrigerators and air conditioners, and so we can encourage governments to do this, and because that increases the availability of high efficiency equipment for consumers. Before handing it over to Adrian, I would say that we finished this report the beginning of 2020, and our company invests in energy efficiency and renewable. And we found that even though this is meant for companies like us, that we are not really applying it because the solutions are complicated, because you have to know a lot about this equipment for that application, and people prefer simple solutions like solar photovoltaics. Just put on solar panels on your roof and you generate electricity, and it's a simple solution. So part of the barrier is that these are complex systems, and how do you promote something that the answer is not simple, right? With that, I'll leave you to Adrian to continue.
Thanks, Gautam. You have one last.
I have one last slide. Okay, one study looked at the potential for climate change mitigation. How much can you reduce how many gigatons of CO2 can you reduce from different technologies? And third from the bottom is electric cars. And the top item on this study is clean cooling. So clean cooling has a large potential for climate change mitigation, especially because this is looking from 2030 to 2050. And this is because the future, there's so much more cooling, the demand is increasing so much that you also have a big potential for doing it right. So you have a huge, and it is kind of less talked about compared to fourth from the bottom, coal-fired power plants, or something in the middle, which is wind energy. I'm not ignoring the others, but clean cooling should also be taken seriously. All right, continue, Adrian.
Okay, thanks, Gautam. So, well, after all this information, I would like to say that we've been talking a lot with Gautam about the content of this report. So we've been analyzing the different abstractions of the know-how presented here, and well, we find that we have high-level abstraction, mid and low-level, kind of the generalist and specialist know-how, and this is really important because it's kind of a proxy of the know-how that you need in a company to build these huge reports. Now Gautam has presented a summary, but they are really complex and with a lot of information, a lot of references. And well, this slide is, then you can check in detail, but it's really impressive. And you actually need a huge interdisciplinary work for making this kind of reports. So, well, you may check also the details after the presentation. I know that the font is very little, the image is very little, but mainly in this image, I describe the flow of the construction of this kind of reports, in which the beneficiary is always different from the organization who pays. It's almost always different. So that is one of the main facts. We can also say that climate change analysts and companies not always have the whole in-house knowledge, so they usually outsource part of the research. And well, the funding is usually also international, and the beneficiary is usually a government or a company, and well, always the planet is through a beneficiary. And maybe we can ask about how much effort the organizations put in disseminating these reports, and if there a centralized database of these reports. Well, and also again about the extrapolation. How can we extrapolate the case studies between cities or between case studies, so we can generate better understanding of the similarities between cities, for example, between damages. So let's go back to the causal loops. So here we have a very simple one, as Gautam explained before. If you install more air conditioning systems, the heat in the streets will get higher, and the people will buy more air conditioning systems. So there we have a positive feedback loop, that if we make the loop, the diagram a little bit more complex, or taking more context on account, for example, the greenhouse gas production will increase the mean seasonal temperature. And well, this kind of diagrams can help to understand some insights, part of the report that Gautam, for example, explained. And well, here we can see the part of the leakages or the refrigerant stock in used air conditioner equipment. So what can we do to make this activity of recovery profitable? So well, maybe with market mechanisms, pricing the activity, the refrigerant recovery, or maybe with some regulations. And well, it's good to say that this kind of diagrams need verification with references, but they really help to understand the whole map. So again, some summary about the abstractions. Gautam talked about some actions. For example, the gas recovery. We can also talk about some maybe final disposal regulations, or installing some other cooling systems, cooling techniques. And well, all these actions, then you can check after the presentation, but we can understand if they are top down or bottom up, depending on different characteristics. For example, if they are regulations, programs, or projects. So if we are expecting, for example, little companies to make business with the gas recovery, going house by house, recovering the gas from the obsolete air conditioning systems. So well, it's a really huge effort. So the last slide. So here we go away again with the diagram from the first part. Remembering the question about why would a government invest in local mitigation actions, the benefits are in the future extremely slow and global, for example. So let's think about the example about the smoking, people smoking inside supermarkets or restaurants. So maybe nowadays it's not easy to find a restaurant or a supermarket in which you can smoke inside, because people are conscious about the damage that smoking makes for all. And so, well, taking this kind of example, we can say that adding the bottom-up pressure to the top-down existing pressure by funding companies to extrapolate case studies. Let's check here in the diagram. We need to achieve local population consciousness. So to get this higher, the bottom-up pressure for local mitigation actions. So here, again, with the question about is the present suffering helps population consciousness, and well, maybe no, because they first need the language tailoring of the case studies and understanding the real problem, the root cause. So only after understanding, they might get the relationship between the government actions in local adaptations and the future, understand the future potential suffering. So after the population gets some consciousness about all this, you will not get the critical mass. So if you get the critical mass in the same example as smoking inside supermarkets, for example, if the local people get that consciousness, they will start, or we will start asking our government to invest more in local mitigation actions. And although the benefit is not tomorrow and exclusively local. And for that, language tailoring or language simplifying the language of this report, you need to fund, I don't know, maybe some companies to make this activity with case study diffusion and extrapolating technology reviews between cities and simplifying all the language in this huge report. So you can achieve that local governments invest more money, although the benefit is not local. And well, here we have the delays, some relation between the blocks and the main relationships. So well, this is kind of one of the systemic conclusions that we need to add the bottom-up strategies to the top-down strategies that we all know that come from global organizations and different scientific groups. So, well, let's maybe think together about that bottom-up strategies for the future. And now, questions and answers, and we leave you with some questions. For example, how can we promote sustainable space cooling? Why is saving the world so slow? And what can systems engineering do for climate change mitigation?